Okay, I think we're good. So, let's start by talking about some average rate of change today. So, I'm going to put a little context to it this time. So let's say that we have just an equation this time. Okay, we've talked about it before with, like, I think the example we did was something about the average rate of change of like an object that is moving or whatever over time, that sort of thing. But in general, we should be able to do this process for just some function that we have. Okay, so we're going to kind of change the context a little bit back into more just like pure math stuff here. So let's say that I have the function x squared minus 5x. And I want to know what is the average rate of change of f of x on the interval 1, 3. And keep in mind that a rate of change is simply a measure of slope. Okay? So it's a measure of slope from one point on the curve to another point on the curve. So if I were to graph this whole curve, I found the point on it at 1, I found a point on it at 3, I drew a line between the two of them, and I wanted to know its slope. Does that make sense? It's essentially what we're doing. Okay? So the average rate of change, if it's a slope, think about it like change in y over change in x. Okay, well the change in y is f of 3 minus f of 1. You plug in the 3, get a y value. You plug in the 1, get a y value. What's the difference? That's the change in that y. And then the change in the x is simply just 3 minus 1. So we end up with this f of minus f of on top, and then just the two numbers subtracted from the interval on the bottom. Okay, so then we got to do a little legwork of actually plugging the numbers in and seeing what we get. So f of 3, let's see if we can do that in our heads real quick here. 3 squared is 9 minus 5 times 3, that's 15. So 9 minus 15 is negative 6. And f of 1, 1 squared is 1 minus 5 times 1. So 1 minus 5, negative 4. So negative 6 minus negative 4 over 3 minus 1. So that's negative 6 plus 4, that's negative 2. 3 minus 1 is 2. So the average rate of change on that interval then would be negative 1. Okay? Or the slope of the secant line, we call it a secant line, is negative 1. Okay? So just to kind of illustrate here what we just did, just so you can kind of see it on a graph. So for this function, f of 1 we found was negative 4. Okay, so that was here. And then we had 3 was at negative 6. Okay, so this curve, I'm not exactly sure what this thing looks like. I mean, it's a parabola opening up. So it's probably doing something kind of like this. Not entirely sure precisely what it looks like, but something kind of like that. So it's curved, right? Well, what we just did was we said, okay, so yeah, if I got this little point that's going along this curve from 1 to 3, so I'm investigating just this little piece of it right here. So as that thing changes, what is its average rate of change, okay, with its position as it goes along there? So like I said, what we just did was we took these 2 points, connected them together with a little line segment, and we just figured out what the slope of that line segment is. Okay? So we found the slope of the secant line. It's called a secant line. So if you're asked to find the slope of the secant line or an average rate of change, you're doing the same thing. Okay? Now, usually we're not so interested in average rate of change. We're more interested in instantaneous rate of change, which we've looked at a little bit. An instantaneous rate of change would be taking these 2 endpoints of this interval and smashing them together at one point. So just at one specific point, what's happening? Okay? So we're going to repeat this process, but we're going to figure out what is the slope of the tangent line, or what is the instantaneous rate of change at, let's say, exactly 3. Okay? So same function, kind of a different goal this time, though. Okay, so what is the instantaneous rate of change, then, of f of x at x equals 3? So when we're talking instantaneous rate of change, remember that's at one specific spot. It's not over an interval anymore. Okay, it's not an average. It's exactly what is the rate of change at a specific spot. Okay, and we talked about that assume h was some kind of like teeny tiny increase in where we were at. Okay, and then we wanted that h essentially to be 0. And we came up with this limit definition here that said it's the limit as h goes to 0 of f of x plus h minus f of x divided by h. And we talked about how this has a special name. It's called a difference quotient. You don't really need to remember that per se. It's just, can you use it the right way? So for us, for this one then, what we want to do is we want to calculate the limit as h goes to 0 where x is 3, because we're interested in what's the instantaneous rate of change when x is equal to 3. So we're going to do f of 3 plus h minus f of 3 all divided by h. Okay, so we're going to do that limit calculation. So f of 3 plus h. All right, well, got to go to our function that we've got up top there and start plugging that stuff in. So that's going to be 3 plus h squared minus 5 times 3 plus h. Okay, so that all right there is my f of 3 plus h. And then I got to subtract from that f of 3. And f of 3, we've actually already done. We got what? Negative 6 for that, right? 9 minus 15? Yeah. So then this would be plus 6. All divided by h. And then we got to whip out our algebra skills here and multiply that stuff all out. Okay, so 3 plus h squared. Just going to start with that. So that's 9 plus 3 times h plus 3 times h, 6h plus h squared. And then distribute the negative 5, so minus 15 minus 5h. And then we've still got the plus 6 on there. all that divided by h. And then we can start canceling stuff out on there. So let's see, 9 minus 15 is negative 6, plus 6, so that's all. These are all essentially canceling out. And then we've got 6h minus 5h. So we've got the limit as h goes to 0 of h plus h squared. Still divided by h. So we start canceling our h's there. Then we've got the limit as h goes to 0 of 1 plus h. How did the what? The 9? What's 9 minus 15? Negative 6. Plus 6. So those are all gone. All right, so then I distributed that h, divided it out of both terms. So what's the answer now? What's the limit as h goes to 0 of 1 plus h? Just 1, right? Because you can plug it in now. So it's just 1. So what that means is at 3, we have a slope, an instantaneous slope of 1. So that tells us a little something about the curve at that particular point. So I'm going to come back to my little graph here. So remember, we've got this parabola-looking thing. So that means that when I'm at 3, which is maybe like here somewhere, here's my point. That means that that has a slope of 1. Well, how in the world can I show a slope when it's just 1 point? Okay, well, I have to have not a secant line like the last one, but a tangent line. So the line is still going to hit the curve, but it's only going to hit it at 1 point. That's what a tangent line does. And it has to have a slope of 1. So it's going to be something maybe kind of sort of like this. Okay, so do you guys see, like, if I had a bunch of tangent lines through here, that all my tangent lines at this point in the curve would be negative, or their slopes would be negative, right, as I'm coming down? And then as this thing starts to curve, these tangent lines start to level off. And then as soon as I come back up right here, now I've got a slope of 1 when I get to 3. Okay, so it's starting to head up. I had this really cool applet that showed you all this, but again, it didn't work, so I can't. But anyway, so that's kind of the idea, though, is that the instantaneous rate of change tells you something about a tangent line, the slope of the tangent line at that particular spot. Yeah?
When you were at the limit is 1 plus h,
yeah.
What did you plug in to find 1?
0. Because we're doing the limit as h goes to 0. And the only reason I didn't plug in before that is because of the denominator, right? As soon as I cancel that, then I'm good to go. Yeah. Okay. So are we okay with that tangent line connection, though? That we're finding a slope of that tangent line at that particular spot when we do this? Okay, that's that kind of key connection from the graph to this whole calculation stuff that we're doing. Okay, finding a slope of a tangent line. So you might be asked a question, what is the instantaneous rate of change at a particular spot? Or you might be asked, what is the slope of the tangent line at a specific spot? Okay, it means the same thing. Just like finding the slope of a secant and doing the average rate of change is the same thing. Doing an instantaneous rate of change and the tangent line, that's the same thing too. Okay, so I'm going to have you guys do one of these for me.